Alright guys, welcome back to another video. It's been a minute because I've been working out problems and I've also been working a lot, but we're back. So in this video I'm going to be going over problems that are at the end of chapter 3, which is what the last video was about, but I'm going to be going over some problems that are not as obvious as the ones we've been doing. So these are a little trickier. So I'm gonna choose maybe like 3 or 4 to do. But okay, we'll start. We'll go ahead and start. So I think the first problem I want to do is I guess we'll start with this one. Okay. Alright, so the problem says, there are 97 men and 3 women in an organization. A committee of 5 people is chosen at random, and one of these 5 is randomly designated as chairperson. What is the probability that the committee includes all 3 women and has one of the women as chairperson? Okay, so a couple things to consider. So we have that a organization has 97 men and 3 women. So obviously that is 100 total people. Right? Okay, and that's just from the first line of text. Okay, a committee of 5 people is chosen at random, and one of these 5 is randomly designated as chairperson. Okay. The question again asks, what is the probability that the committee includes all 3 women and has one of the women as chairperson? Okay, so this sounds like we're trying to find the probability of 2 events happening at the same time, right? Because we're trying to find a committee that includes all 3 women and that same committee has a woman as a chairperson. Okay, so we have a couple events to consider, right? So event A, we'll say, is the event that the committee has a woman as a chairperson. Right? And event B will say that the committee has all 3 women. Yes. Right? And hopefully you guys can see that. Okay. So, right, we're trying to find the probability of both of these events happening. So remember that we're trying to look for the probability of A intersect B. Excuse me. Now, if you'll recall from a previous chapter, one way to find this probability is to find the probability of A given B times the probability of B. Alright. So we'll be using this formula. This is just from like a chapter ago. Okay. So, alright. So now what we have to do, we have to find these probabilities in order to find this one that we're looking for, right? Okay. So what is the probability of A given B? So if we were to read that out, what is the probability that a committee has a woman as a chairperson, given that the committee has all 3 women? Well, if a committee can only have 5 people, and we're given that the committee has all 3 women, then that means that there is a 3/5 chance that the committee has the woman as a chairperson, right? And that goes back to what the question says. A committee of 5 people is chosen, and one of these 5 is randomly designated as a chairperson. So in order to find this probability of A given B, we're given B, right? The committee has all 3 women. So what's the probability that the committee has a woman as a chairperson? Again, that's 3/5. Perfect. All right, so we found one part. So the probability of A given B is equal to 3/5. Okay. All right. So now what we have to do is we have to find the probability of B. We have to find the probability that the committee has all 3 women. And in order to do that, we need to think sort of like we have to think broadly. I guess we have to what I mean by that is we have to look at how many possible committees have all 3 women, right? Okay, so first we have to consider how many committees we can make, and that's gonna be our denominator. Whenever we were trying to find the total possible outcomes, right? Okay, so how many possible 5-people committees can we make? Well, that would be, if we have 100 people in total, that would be 100 choose 5, right? And that is, well, here, I'll write it out. I need my calculator. So 100 choose 5. Ooh, it's a big number. Well, I'll write it out anyway. But it's, what is it, 75 million? Yes. 75,287,520. This is how many possible 5-people committees we can make out of the 100 people, right? The total number of combinations. But, well, I'll keep that up. I'm not going to use this big giant number in the answer. I'll just use this as 100 choose 5. So, okay, again, this is how many possible 5-person committees we can make from 100 people. Now we have to consider how many committees, how many 5-person committees there exist that have all 3 women. So if we have, so let's say that we do have all 3 women in the committee already, right? So we have 1 woman, 2, 3, and then we have 2 open slots, right? So in order to find how many committees already have all 3 women, these 2 vacant slots need to be occupied by a couple of men. And in order to find this number, then because we've already taken 3 people out of the 100 total people, then that leaves us with 97. So the total amount of committees that already have all 3 women would be 97. And again, 2 open slots for men, so 97 choose 2. And this is how many possible committees have, this is how many total committees have all 3 women already included. And like I said, those 2 vacant slots would be for 2 men. So there are 97 choose 2 possible committees that have all 3 women. And that is 97 choose 2, 4,656. 4,656. All right. Okay. So I'll kind of divide this right here. So we're going to be using these two probabilities, or these two numbers here, to find the probability of B, that the committee has all three women. So again, in order to do that, this is going to be our denominator, because this is how many total committees have, this is how many total possible committees we can make, and we're trying to find how many have, what's the probability that we have a committee that has all three women. So it would be this number over this one. And I think I'm just gonna, well, for the way it's written, like the way the answer choices are presented, they're kind of written in this form already. They don't use these big numbers because I guess that's just gonna take up too much space in like text. So what they do is they just leave they leave the answers like this. So the probability of B in this case would be 97 choose 2 over 100 choose 5. All right, so boom, we have the probability of A given B and the probability of B. That means that the probability of A intersect B is 3 over 5 times 97 choose 97 choose 2 over 100 choose 5. That is our answer right there. So again, to recap, this is the probability that a committee has a woman as a chairperson, given that the committee has all three women, right? 3 over 5. And the probability of B is the probability of a committee having all three women, and in order to do that, we need to find the total number of possible committees we can make out of 100 people, where we only choose 5, and we find all of the committees that have all three women. And so in order to find the probability of a committee having 3 women, then we would put this number over this one, and then at the end we multiply these two fractions together. Okay, that one wasn't too bad. All right, we'll go on to the next one. Let's see. Okay, we'll do this one that includes like taking balls in and balls out from urns. Or I guess boxes. Okay. So a box contains 4 red balls and 6 white balls. A sample of size 3 is drawn without replacement from the box. What is the probability of obtaining 1 red ball and 2 white balls, given that at least 2 of the balls in the sample are white? Okay, so we'll kind of draw this out, I guess. So we have a box, and it has 4 red, 1, 2, 3, 4, and 6 white balls. 1, 2, 3, 4, 5, 6. Okay, so it says that a sample of size 3 is drawn without replacement. Okay, so we're taking 3 balls out of this box. We don't know which 3, but we're taking 3. And then it says, what is the probability of obtaining 1 red ball and 2 white balls, given that at least 2 of the balls in the sample are white? Okay, so again, we have to consider a couple scenarios. So scenario A, well first, like one of the first event that it describes is obtaining 1 red ball and 2 white balls. So that will be event A. So event A will be the probability of obtaining 1 red and 2 white balls. All right. Now we also, there's also a second event that occurs, or a second thing we have to consider. The last part of this question says, given that at least 2 of the balls in the sample are white. Okay, so that's the other thing. At least 2 of the balls are white. At least 2 balls are white. All right. So, this is kind of like the other question that we just did, except this is now, we're trying to find the probability of oh shoot, what's it called? Of a conditional probability, right? Because the way the question asks it, what is the probability of obtaining 1 red ball and 2 white balls, given that at least 2 of the balls in the sample are white? So what we're trying to solve for is the probability of A given B, and remember this is equal to the probability of A intersect B over the probability of B. All right, so we have to solve for these 2 probabilities right here in order to find this one. Okay, so all right, so we'll solve for this first. We'll solve for the probability of B first. At least 2 of the balls in our sample are white. Okay, since it says at least 2, that means that either we pull out 2 white balls and 1 red, or we pull out 3 white balls and 0 red, right? Because since it's asking at least 2 of them, then we also have to consider the situation where we pull 3 white balls out, because that's still at least 2. At least 2 of those are white. We pulled out 3 white balls, but at least 2 of them were white. So this is a couple of things to sort of keep in mind whenever we're solving for this probability, for the probability of B. So I'll write them down. So scenario 1, we pull out 1 red and 2 white balls. All right. So in order to find this, whenever we're trying to find this probability, then what we do is, okay, what's the probability that this happens, right? So if we're choosing 1 red ball, well, we have 4 in the box, so that gives us a 4 choose 1 probability, and then we multiply that by the probability of pulling out 2 white balls. There's 6 to choose from, so that's a 6 choose 2. And if you put this in a calculator, 4 choose 1 is 4, because there's 4 ways to choose 1 red ball. 6 choose 2 is 15. There are 15 ways to choose 2 red balls from 6 total red balls. So that is equal to 60. All right, so that's only part of it. This is only part of probability B. We also have to consider scenario number 2, where we don't get a red ball and we pull 3 white balls, right? At least 2 balls are white. Well, we pulled out 3, at least 2 of them were white, even though we pulled out 3. And also remember that we're pulling 3 because that's the sample size that it asks for in the question. Okay, so pretty much solving it like this. How do we choose 0 red balls? let's for choose 0, and then multiply by the probability. How many ways can we choose 3 white balls from 6 total? 6 choose 3. 4 choose 0, that's 1. 6 choose 3 is 20. So this is 20. All right. Okay, perfect. Now, and again, this is kind of like, well, I'll keep it like this for now. Okay, so we have considered both scenarios for probability of B where we pulled at least 2 white balls, right? These are the only 2 situations where this happens. So we're good. We've solved for probability of B. Well, we're going to use these numbers in order to find this. So yes, we've solved for the probability of B, but in the context of this, we're not done yet. Okay, so we'll leave B alone for now. Now what we want to find is the probability of A intersect B. Okay. And remember, if we read that to ourselves, what is the probability of obtaining 1 red ball and 2 white balls, and at least 2 of them are white? Well, that would just be this right here. This scenario in this case. Whenever we solve for the whenever we were trying to find the probability of B, and we thought about the scenario where we pull 1 red and 2 white, well, at least 2 of the balls are white. Okay, we got that right here. And the probability of obtaining 1 red ball and 2 white balls, well, that's what we solved for in this scenario. So it's basically this exact same thing right here. This right here answers both of these questions, right? Because the probability of obtaining 1 red and 2 white balls, and at least 2 of the balls are white, well, here we have pulling 1 red and 2 white balls, at least 2 of the balls are white, so it's this right here again. So we didn't have to find like a different probability. We already solved it whenever we were trying to solve for the probability of B. This scenario right here addresses both of these things, which is this probability up here. Okay, so we're done. We have to construct this now. So how do we do that? Well, the probability of A intersect B is 4 choose 1 times 6 choose 2. 4 choose 1 times 6 choose 2 over the probability of B. And it's these two added together because that's the total probability of B. So it's 4 choose 1 times 6 choose 2 plus 4 choose 0 times 6 choose 3. If it's a little small, I'm really sorry, but that's it. That is it. That is the probability of A given B right up here. So again, we solve for B first by considering the scenarios, every scenario where we at least pull 2 white balls. So we either pull 1 red and 2 white, or we pull 0 red and 3 white. Both scenarios, at least 2 of the balls are white. And then whenever we were trying to solve for this probability intersection up here of A intersect B, well, this first scenario, whenever we were solving for the probability of B, answers to both of these events right here. And so, boom, that's our numerator. And that's their answer right there. Pretty easy, but they get harder. I was having trouble with some of these. You just gotta read them like over and over and kind of make sure you understand them in your head. Also, the wording can be kind of confusing sometimes. Okay, we'll do this next one. they're like confusing when you read them, and then once you're done like working it out, you question why you thought it was hard. I don't know. Okay, we'll do this one next. We'll probably do like a couple more. Well, yeah, maybe this one. Alright, well, we'll just do like three. They're not like, again, they're hard whenever you first read them, but then the process is actually pretty easy. Alright. A box contains 35 gems, 10 are real and 25 are fake. Gems are randomly taken out of the box without replacement. What is the probability that exactly 2 fakes are selected before the second real diamond is selected? Okay, so let's go back and reread this kind of. Excuse me. Okay. So, okay. So what is the probability that exactly 2 fakes are selected before the second real diamond is selected? So we have to pull out 2 fakes, and then that happens before we pull a second real one, which means that there's a first real one that we've already pulled. So in total we've pulled 4 diamonds. Okay. Or 4 gems. It doesn't say they're diamonds, but well. Okay, so I'll write down what we know. So 35 gems total, 10 real, and 25 fake. Okay, so the probability that we pull out 2 fakes before the second real one. Alright, so this isn't a like conditional probability or like an intersect probability, it's just a probability that we have to find. So we won't solve this like we've solved these past few ones. Okay, so again, we pull out 2 fakes before a second real, which means that there's a first real that we've already pulled. It just doesn't say it explicitly in the question. So there are 4 diamonds to consider. Now, the order of pulling the gems matters a lot, because pull 2 fakes before the second reel. Okay, so the second reel has to be at the end. Reel number 2. R for real. The order that we pull these gems out matters a lot. Because we've pulled 2 fakes before a second reel, and we've already pulled the first reel, that means that the second reel has to be at the end of this chain. And I guess we can just fill in these however way we want for now. So we'll say we pulled the first reel over here, and then we pulled out the first fake, and then the second fake, right? This is only one way of doing this. Because what if we pulled out, the first reel, or the first fake, and then the first reel, and then the second fake, right? That's another way. So I'll write that one down. So again, reel number 2 at the end, fake number 1 at the start this time, and then we'll say reel number 1 follows, and then fake number 2 follows. All right, that's another way of pulling these gems out in a different order. Oh, but what about if we pulled the fakes out first, and then the first reel, and then the second reel? That's still another way. So real number 2 at the end. So we pulled out the first fake, fake number 1, and then we pulled out fake number 2, and then finally real number 1, and then real number 2. So there are 3 different ways of having real number 2 be the 4th gem pulled, or like the question asks, pulling 2 fakes before the second real one, right? There are 3 different ways of doing that. There are 3 different ways of pulling 2 fake gems before a second real one. And, okay, I mean, how do we find the probability of this happening now? Well, in every single scenario, or in every single, scenario right here, we multiply the probabilities. We're not replacing the gems either, so we're pulling one out and then like setting it aside. So that means that the total number of gems in the box decreases, and we have to consider that as well. So we'll start with this first chain of events right here. What's the probability that we pull out a real gem from the box? Well, since there are 10 real and there's 35 total, that would be 10 over 35. All right, and that's just for this first real gem right here. And that's followed by our first fake gem. So what's the probability that we pull a fake gem from the box? Well, we've already pulled out one of the gems. That means that there are 34 gems left. There's not 35. And it's our first fake, so there's still 25 fake. Okay, so this gets multiplied by 25 over 34. And we're going to do this for all of these, for the rest of these scenarios, you know? All right, so we've already pulled a real gem, then we pulled out a fake gem. Now what's the probability of us pulling out another fake gem? Well, again, the total goes down by 1 again, so there's 33 gems left. We've already pulled out 1 fake. That means that there are 24 fakes left, so 24 over 33. And then finally, what's the probability of us pulling out the second real gem finally? Again, total goes down by 1. That's 32. And we've already pulled out 1 real gem, so that now there's no longer 10, there's 9. Boom. And that's only the probability of this this process right here. A real, a fake, a real. Now we gotta do this exact same thought process to this and this, okay? And it's really the exact same. This multiplication right here is going to be the exact same for these two, and it's just that these are going to be like rearranged in a different way, but you'll see what I mean. All right. What's the probability of us pulling out the first fake? 25 over 35. Times, what's the probability of us pulling out a real? 10 over 34 now, right? Our total goes down by 1. All right, what's the probability of us pulling out another fake? We've already pulled 1 out, so that's 24 over 33. And then finally a second real, 9 over 32. All right. Now we'll do this last chain. What's the probability of us pulling out a first fake? 25 over 35. Followed by a second fake, 24 over 34. What's the probability of us pulling out the first real? 10 over 33. And the second real, 9/32. Okay. Okay. Oops. So, if we multiply all of these three things out, we're gonna get the exact same answer. Multiplication is, oh shoot, what is it? It's like one of the rules. It's, oh, what is it? Multiplication is not conductive. It's, somebody will tell me. Where if we rearrange multiplication terms, even in fraction form, we're still going to get the same thing. And I mean, you can just... Sorry. Sorry. I mean, you can plug these in your calculator and you're going to see you get the exact same thing. Dang, I can't remember the transitive, maybe. So yeah, ultimately these will yield the exact same answer. We'll get the same answer 3 times. So what we can do is we can just multiply one of these by 3. Right? Because we get 3 of the exact same thing. So 3 times, and we'll do like a long big old fraction. So we could do like 25 times 24 times 10 times 9 over 35 times 34 times 33 times 32. And that is our answer. If you multiply this out, you get 675 over 5236. That's our answer. So the probability that we pull 2 fakes before a second real gem is 675 over 5,236, which equals 5,236 0.129. This was rounded. Okay, so again, just to quickly recap, we have to pull out 2 fakes before a second reel. That means that there's a first reel that we have pulled out already. So we're pulling 4 gems out in total, but we have to think about every possible combination of real gems and fake gems where we get a second real gem at the end, right? So we have to rearrange the fakes and that first reel, and we multiply out the probabilities of each gem getting pulled. Again, there are 3 different combinations of doing this. Each of these multiplications gives us the exact same thing, so we can just multiply one of these by 3, which gives us our answer. Alright. And again, this wasn't like a conditional probability or like intersection probability, so it's just straightforward fractions, you know. The hardest part is definitely trying to like set up the problem, because again, I guess well, like for me, the first time I did it, like I only considered like one of these, and then I didn't get the answer I wanted, so I was like, wait a second, there's more to it. So that is the hard part, is the setup. Okay, let's go on to the next one. Alright, okay. Alright. So, we'll do this one. This one took me a while. That one's just like that. Okay, then maybe that one. All right, we'll do two more. Okay. An insurance company determines that N, capital N, the number of claims received in a week, is a random variable with the probability of N equaling N. I should write this out. Okay. So an insurance company determines that N, which is equal to the number of claims received in a week. Okay, determines that N is a random variable with the probability of capital N equaling lowercase n is equal to 1 over 2 raised to the lowercase n plus 1, where lowercase n is greater than or equal to 0. Alright? The company also determines that the number of claims received in a given week is independent of the number of claims received in any other week. Determine the probability that exactly 7 claims will be received during a given 2-week period. Alright, what the heck does that mean? We're basically solving for that last sentence there. Determine the probability that exactly 7 claims will be received during a given 2-week period. Okay, so in a 2-week period, we have to receive exactly 7 claims. Now, we can split this up where we have week 1 over here and we have week 2 over here. Alright? I'll leave some space at the end for something. Okay, so across 2 weeks, a company has to receive exactly 7 claims. How can we split that up? Well, there are 8 ways of splitting it up, actually. So in order for us to receive exactly 7 claims across 2 weeks, in week 1, we could get 0 claims, and then in week 2 get all 7. That's one way. That's one way of doing that, right? 0 claims. And then in week 2 we get 7 claims. Right? That's just one way of doing it. Oh, what about week 1 we get 1 claim, and then week 2 we get 6? That's still exactly 7 claims. 1 claim, and we get 6 claims. I'm also gonna separate these out with a line like that. Right? And we're just gonna go down the list doing this. And that's gonna give us all of the possible ways of getting exactly 7 claims across a 2-week period. We just gotta, split the 7 up, like how we're doing. I mean, okay, what would be the next scenario? Oh, we get 2 claims in week 1, and then we get 5 claims in week 2. That's exactly 7 claims. And we're just gonna keep doing this. So 2 claims, and then 5 claims. Boom. Week 1 we get 3, week 2 we get 4, that's still 7. I don't want it to go off the screen. Okay, I'm fine. 4 claims. And then we'd start going up here, going down here. 5 claims, 2 claims, 6 claims, 1 claim, 7 claims, and 0 claims. Oop. Oop. Alright, so these are all the possible ways of splitting up exactly 7 claims over a 2-week period. Now, how do we use this? They gave us this for a reason, but how do we use it? Well, it tells us that capital N is equal to lowercase n. And it also told us that capital N is the number of claims received in a week. So if we're trying to find the probability of 0 claims happening, then we would use this fraction of 1 over 2 raised to the n plus 1, and we would replace that lowercase n with the number of claims that we received in a given week. And also we're allowed to use 0 here because it says here n is greater than or equal to 0. So, excuse me. So what does that mean? What do I mean by that? Again, what's the probability that we get 0 claims in week 1? Well, using this fraction right here, it would be 1 over 2, and remember, lowercase n is equal to capital N, and capital N is equal to the number of claims, so that would just be 2 raised to the 0 plus 1, or 1/2. If you know, 0 plus 1 is 1, 2 raised to the 1 is still 2, so this is 1/2. All right. What about if we received 1 claim in week? Well, okay, instead of moving down, let's go across. So for week 1, the probability of receiving 0 claims is 1/2, because we replaced that lowercase n with the number of claims, and then we just solved the exponent and then got 1/2. What about 7 claims? What's the probability of us getting 7 claims in week 2? That would be 1 over 2 raised to the 7 plus 1, or 2 to the 8th. 1 over, what's 2 to the 8th? 64? I think. Is it? Hold on. 2 raised to the 8th. 256. So this is, well, we'll keep it 1 over 2 to the 8th, and you'll see why in a second. And we'll just explicitly say that there's a 1 right there. Okay. And then we're just gonna do this for all of them, for all of the rest of these claims. So what's the probability that we get 1 claim in week 1? 1 over 2 raised to the 1 plus 1. That's just 1 over 2 raised to the 2. Right? Now, what's the probability that we get 6 claims in week 2? That is 1 over 2 raised to the 6 plus 1, or 1 over 2 to the 7. And it's just going to follow this exact same pattern. This exponent on week 1 is going to go up by 1, and the exponent on week 2 is going to go down by 1 each time. So, this is going to be 1 over 2 to the 3rd. This is going to be 1 over 2 to the 4th. 1 over 2 to the 5th. 1 over 2 to the 6th. 1 over 2 to the 7th. 1 over 2 to the 8th. And over here, 1 over 2 to the 6th. 1 over 2 to the 5th. 1 over 2 to the 4th. 1 over 2 to the 3rd. 1 over 2 to the 2, 1 over 2 to the 1st, or 2 to the 2nd. All right. So, I mean, yeah, once you solve for a couple, you can notice where the trend is going. So that's why I just, skipped adding to the exponent, and I just went straight ahead to the answer. Same thing over here. Okay. Now we've gotten individual probabilities for week 1 and week 2. But what are the combined probabilities, right? Because we want to find the probability across the 2-week period, not just for week 1 separately and week 2 separately. So we got to combine these probabilities. So the combined probability of this first case right here, if we add 1 over 2 to the first to 1 over 2 to the eighth, that gives us 1 over 2 to the ninth. Right? This probability plus this probability, 1 over 2 to the ninth. Alright, what about this case right here? 1 claim plus 6 claims. 1 over 2 to the second plus 1 over 2 to the seventh is equal to, oh look at that, 1 over 2 to the ninth. Again, this probability plus this probability, 1 over 2 to the ninth. And you guessed it, it's going to be 1 over 2 to the ninth for all of these. 1 over 2 to the ninth is going to be the combined probabilities of every single one of these 2-week period scenarios. So that answer is going to go for all of these. So that gives us 1, 2, 3, 4, 5, 6, 7, 8. 8 times 1 over 2 to the ninth. Right? 8 because there are 8 different cases of 2-week periods. And then 1 over 2 to the ninth because it's going to be the combined probability of week 1 and week 2 in this case, in this case, in this case, in all of these. And there's 8 of them. And that is the answer. It's 1 over 64 if you've multiplied it out. So that is the probability of exactly 7 claims that's a probability that we received exactly 7 claims over a 2-week period. But again, we have to think about how many possible ways can we receive 7 claims over a 2-week period. So we split up 7 claims across a 2-week period 8 different times. We got the same probability each time, the same combined probability each time. And because there's 8 of them, well, we multiply that combined probability by 8, 1 over 64. So, yeah, this is our answer right here. Oh, my stomach's rumbling. I drank too much milk earlier. So yeah, that's how you would solve this one. It's, again, you just got to think about all the possible scenarios. You can't just think it's, one and done, right? All right. Let's go on to the next one. I hope this is making sense. It's starting to make more sense to me, for sure. Okay, we'll go to the last one. This will be the last one that we do. Okay, let's see, which one do I want to try and do? Maybe this one. Yeah, we'll do this one. Okay, this will be the last one. Okay. 3 boxes are numbered 1, 2, and 3. Alright, so let's go ahead and put it up here. So we've got box 1, box 2, and box 3. Alright. For K equals 1, 2, or 3, box K contains K blue marbles and 5 minus K red marbles. Okay, so that basically means that for any box we choose, it has the same amount of red marbles, or blue marbles, and 5 minus K red marbles. So, I'll write it right here. For box 1, we have 1 blue, and then K minus 1, 5 minus K, 5 minus 1, which is 4 red marbles. Box 2 has K blue marbles, K equals 2, 2 blue marbles. 5 minus K, 5 minus 2, 3 red marbles. And same for box 3. K blue, K equals 3, 3 blue. 5 minus K, 5 minus 3 is 2, 2 red. Alright, so this is how the boxes are, this is how many marbles of each kind are in each box. Okay, in a two-step experiment, a box is selected and 2 marbles are drawn without replacement. If the probability of selecting box K is proportional to K, what is the probability that the 2 marbles drawn have different colors? All right. So this one is a little tricky. Okay. How do I want to start this? Damn, my stomach is acting up. Okay. Let's. Okay, something we have to consider is that it says that the probability of selecting each box is proportional to K. What does that mean? That means that, let's say that the probability of selecting box 1 is P. So P is equal to the probability of selecting box 1. Right? If selecting a box is proportional to K, in this case, K is 1, 2, or 3, that means that the probability of selecting box 2 is 2P. That is the probability of selecting box 2. Which means that the probability of selecting box 3 is 3P. Alright, now because we have to choose a box in this experiment, the probability, if we add up these probabilities, it's just going to equal 1 because we have to choose a box. So P plus 2P plus 3P is equal to 1. 1 is the total probability of a box being chosen, which in this case is 100. There is a 100% chance of us choosing a box. But we have to add up the probabilities of each box individually, and we get 1. And if we solved for P, we get that P is equal to 1 over 6. Oops. Okay. Keep this in mind. We'll use this later. This 1 over 6 right here. Okay. Oh, also, again, that's the probability of selecting box 1. If we were to replace this P right here with 1/6, then the probability of selecting box 2 would be 1/3, and the probability of selecting box 3 would be 1/2. But we won't use this just yet, but we will. Okay. So we're trying to find the probability that 2 marbles that are drawn are different colors out of each box. So because each box has a different probability of being chosen, we're not going to use the exact same probability each time. You'll see what I mean. Okay, I'm just going to write what we need to find. Okay, so we're trying to find the probability of 2 different colors, two different colored marbles. Chosen, given that box 1 is selected. Hold on. Okay, yeah. Times probability of box 1 selected. Okay. This, I guess this would be considered a conditional probability, so we're trying to find the intersection of two different colors being chosen and box 1 being chosen. Now, normally, I guess we could have stopped here, except we have to remember that the probabilities of a box being chosen is proportional. And what that does to the way we're trying to solve is we have to solve now an individual probability of like box 2 being chosen, right? So now we have to add the probability of two different colors given that box 2 is selected times the probability of box 2 selected plus the same thing for box 3. Two different colors given box 3 selected times the probability of box 3 selected. Okay. This looks a little messy. And it is. So we have to find the probability of two different colors being chosen given that we selected box 1 times the probability of box 1 selected plus the same probability of two different colors given box 2 selected times the probability of box 2 being selected plus the probability of finding two different colors given that box 3 is selected times the probability of box 3 being selected. Okay. These probabilities that are being multiplied at the end of each line, that's where this 1/6 comes from. So again, the probability that box 1 is selected, we already solved for that. That's 1/6. So I will maybe rewrite it down here. So the probability of box 1 being selected is equal to 1/6. Okay. The probability of box 2 being selected is 2p. 2 times 1/6. 2/6, 1/3. And the probability of box 3 being selected is 3p. 3 times 1/6, 3/6, 1/2. All right. So we've already taken care of this, this, and this. Now we have to find these conditional probabilities right here. Okay. Okay, so we've already solved for box 1 being selected. So a conditional probability is, again, it is, let me erase this, I think. And I'll erase this because we already used this. We've already solved for that. Okay. So we're trying to find conditional probability A given B that is equal to A intersect B over the probability of B. Okay. So we already have probability of B. Ooh, hold on. Let me actually, Okay, maybe I'll keep it like this actually. Okay, so the probability of B, what did I say, was 1/6. Okay. So 1/6 is our denominator here. Now, if each box one has 5 marbles total, right? What is the probability of us choosing, and we were choosing 2 marbles, right? 2 marbles are drawn without replacement, so that's 5 choose 2. So there are 5 choose 2, which is, well, we'll keep it 5 choose 2. That's how many different ways we can choose 2 marbles out of a total of 5. But if we're trying to get 2 that are different colors, wait, I think I messed myself up here. Let me erase this. Okay. Our denominator would be the 5 choose 2, because that's how many total ways we can select 2 marbles without any, like, like, oh, one needs to be red, one needs to be blue, or whatever. Alright, so 5 choose 2. Now, what's the probability that we get 1 blue? Well, that would just be 1 over this, right? What's 5 choose 2? Maybe I do need to solve it for it, actually. 10, okay. So 5 choose 2 is equal to 10. Right, now let me rewrite this. 5 choose 2 is equal to 10. Alright. So, yeah, if we're trying to get a different color now, if we're trying to solve for, like, how many ways we can get one red or 1 blue, that would just be 1 over 10, right? Because how do I want to explain this? How am I trying to explain this? So there are 10 possible ways of choosing 2 marbles from a total of 5. And if we want to get a blue one, it's 1 over 5, but because we're saying that there's 10 different ways to do it, let me look at my textbook real quick. trying to like explain this. Oh my god, guys. Dang. I think I just confused myself. Okay, let me. Okay, if we pull a blue marble out first, then that is a 1 in 5 chance of that happening. If we pull out a red one after, then that's a 100% chance of happening. But if we pull out a red one first, that's a 4/5 chance. And then if we pull a blue one out, that's a 1/4 chance. So what is that? What's 1/5? What's 4/5 times 1/4? 1/5 plus 1/5 is 2/5. Wait. No, that's 1/5 plus 1/5. That's 2/5, which is 4/10. And the 10 we said is from that. Okay, yes, okay. I think I might be able to explain this in a different way. Okay. So, okay. In box 1, if we pull the blue marble out first, okay, so box 1, scenario 1. So, if we pull the blue marble out first, then that is a 1/5 probability of that happening, right? Because there's 1 blue, 5 total. Okay. If we pull the red one out second, then that is a 100% chance because there's 4 left and they're all red, so that's just 1. All right. Scenario 2. If we pull the red one out first, that is a 4 in 5 chance happening. And if we pull the blue second, that is a 1 in 4 chance happening. All right. Now, what is the total probability of scenario 1? If we multiply these two together, it's 1/5. What is the total probability of scenario 2? If we multiply these probabilities, that is, what was it? I think it was also 1/5, yeah. Now, what's the total probability of box 1? What's the total probability of the marble pulling from box 1? We would add, so these get multiplied, these get added together. That is 2/5. Okay. We will need this. Dang, I had my, oh, it's right here. Okay, oops. 2/5. Okay, now box 2, scenario 1. Let's say we pull a blue first. that's a 2 in 5 chance. And then the red second. So there's 3 reds. Our total goes down by 1. That's a 3 in 4 chance. Alright. Scenario 2. We pull the red first. That is a 3 in 5 chance. And then the blue second. That is a 2 in 4 or 1/2 chance. Okay, these fractions for scenario 1 get multiplied. 2 over 5 times 3 over 4. That is 3/10. And then these two for scenario 2 get multiplied. 3 over 5 times 1/2 is also 3/10. And now these get added together. 6 over 10, which is 3/5. Alright. And that is the total probability of marble pulling for box 2. Now box 3. I'll kind of... Okay, so box 3. Scenario 1. So box 3 has 3 blue and 2 red. Okay, so in scenario 1 of box 3, if we pull the blue one out first, that is a 3 in 5 chance happening. If we pull the red one second, that is a 1/2, 2 over 4, 1/2 chance. Okay, scenario 2, if we pull the red first, then that is a 2 in 5 chance happening. And if we pull the blue one second, that is a 3 in 4 chance happening. So 3/5 times 1/2 is 3/10. 2/5 times 3/4 is also 3/10. 3/10 plus 3/10 is 6/10, 3 over 5. Alright. What we have done now is we have considered the scenarios in each individual box where we either pull the red one out first and then the blue, or we pull the blue one out first and then the red. And when we're within each scenario, we multiply the probabilities, but then whenever we combine the scenarios, we have to add them. Alright? So, we've solved for both scenarios in box 1, box 2, and box 3. And that is the probability. These are the conditional probabilities that we needed here. The probability of choosing 2 different colored marbles, given that we chose box 1, that's 2/5. Okay, so now we can begin to write out this long thing right here. Okay, the probability that we selected 2 different colors, 2 different colored marbles, given that we chose box 1, is 2/5. And that gets multiplied by the probability of box 1 being selected, which was 1/6. Plus the probability of 2 different colors being chosen given box 2 was selected is 3/5. Times the probability of box 2 selected is 1/3. Plus the probability of 2 different colored marbles being chosen given box 3 was selected is 3/5. Times the probability of box 3 being selected is 1/2. And that all equals 17 over 30. And that is our answer. The textbook solved it in a different way. They actually did use like the 5 choose 2 as the denominator, but I couldn't really explain well how to do it that way. And also it didn't make too much sense to me. And so what I ended up doing was basically this, which I guess maybe is more time consuming, but at least I could see like where each number came from, right? Because I mean, yeah, you have to consider like the probabilities change depending on which marble gets chosen first. So this is the way that I did it. Which, like I said, maybe it looks like more work, but it's not hard work. I mean, these fractions aren't very big. It's just, again, you have to really, really consider every single scenario. And then also remember that the probability of a box being chosen is proportional to the number of the box. That's why these probabilities are all different. Each box has a different probability of being chosen. And then at the end we, again, multiply within the scenarios and then add the total probabilities together. That is it. So yeah, that's how I solved this one. And I still got the same answer as the textbook, so. Okay, I'm done here. For now, I'm gonna do like a million more problems. Maybe I'll start chapter 4 today, maybe. But okay, that's it for this video.